Hello guys, this is Avinash. I am back with another video, part 2 of electromagnetism. Ohm's law. People used to think that is there a relationship between potential difference and current? The answer is yes. In 1960, by a German physicist named George Simon Ohm, found a relation between current flowing through a conductor and a potential difference at the ends. But the condition he put that all physical condition remaining the same for the potential difference is directly proportional to the current flowing through it. That is, V is directly proportional to I, or V is equal to IR, where R is a constant of proportionality and resistance, or is equal to resistance, which remains same for a conductor. Have you got it now? Next slide, please. Heating effect of an electric current. We know that a battery or a cell is a source of electrical energy. Thus, they generate potential difference between the terminals. We know that battery or cell are a source of electrical energy, and thus they generate potential difference between the terminals. We also know that current source must expand the energy. A part of source energy is used in maintaining the current. Obviously, if the electrical energy is produced, then it has to be used in maintaining the current, while the rest part heats the gadget. This is known as the heating effect of current, electric current, that the heat produced due to the extra energy. It is used in devices like electric iron and electric heater. Heating effect is not a bad at all. It is used in some devices like electric iron and electric heater. Formula is P is equal to V into Q by T. We know that I is equal to Q by T. I is equal to charge by time. That is equal to Vi equal to power input. H is heat produced in time T. H is equal to V into I into T. By putting the V is equal Vi into T, H is equal to I square R T. We know that V is equal to IR by Ohm's law. In the previous slide only we discussed that. Here H is equal to I square RT. This is known as Joule's law of heating. Have you got it, no? Okay. Electric power. Electric power, the rate at which the electric energy is consumed in an electric circuit is termed as electric power. Means the rate at which, means it has to be the rate at which the electric energy is consumed. Power P is equal to Vi is equal to I square R is equal to V square R. V we know that IR, that is equal to I square R. I square I is equal to V by R, so V square by R square is equal to R, that is equal to V square by R. SI unit of watt. SI unit is watt of electric power. 1 watt is equal to 1 volt into 1 ampere. Commercial unit of electrical consumption is kilowatt hour, commonly known as 1 unit. 1 kilowatt hour is equal to 1000 watt into 3000 second equal to 3.6 into 10 to the power 6 joule. This is the unit of 1 kilowatt hour. This is 1 unit in which we pay the bills of our home. Magnetic effects of current. That's the next topic, is magnetic effects of current. Hans Christian Ørsted, one of the leading scientists of the 19th century, accidentally in 1820 discovered that a compass needle got deflected when an electric current passed through it. Electric current passed through a metallic wire placed nearby. Through this observation, Ørsted showed that electricity and magnetism were a related phenomena. Hans Christian Ørsted in 19th century by mistakenly accidentally found that a compass needle got deflected when an electric current is passed through a metallic wire. This by mistake theory helped us a lot because it showed the relationship between electricity and magnetism. This is how he set up the experiment. This is a conductor. A plate is shown here. The compass needle is there. This is the key. This is the rheostat. This is the ammeter. Here the current is passed, and when it passed through this plate, the compass needle deflected, and thus he found the relationship between electricity and magnetism. Magnetic field and magnetic field and field lines. We are familiar with the fact that a compass needle gets deflected when brought near a bar magnet. We got from the Oersted only that when the compass needle gets deflected when brought near a bar magnet. No, sorry, not by Oersted. We know by general only, because when a bar magnet is placed, then the compass needle will deflect, because that compass needle consists of north and south. So if you bring the north, that will deflect. If you bring the south, it will attract. That's all. That is all. The compass needle is in fact a small bar magnet only. This is the when iron fillings are placed near a bar magnet, then they constitute this shape, means they attract they shape in the form in they form in the magnetic field lines, like here only you can see the magnetic field lines. South it attracts, north it repels, and this forms a circular type of closed circuit. This is the field lines around a bar magnet, and this is the iron fillings near the bar magnet align themselves along the field lines. Have you got it? This is the magnetic field due to a current carrying conductor. This is a this is a circuit. Okay, this is a circuit. This is the battery. This is the key. This here the compass is placed. The current direction is from this side to this side. So the deflection you can see in the means the north south. It is equal to which direction that would be? This would be northeast, I guess. If this is east, yeah, this should be northeast. But when the battery's direction is changed, means the flow of current is changed, then there is sudden means the deflection of the compass also changes. From the northeast, it changes. Okay, towards north, I guess. Towards north. If this is northeast, means that would be northwest. A simple electric circuit in which a straight copper wire is placed parallel to and over a compass needle, the deflection in the needle becomes opposite when the direction of current is reversed. As you saw also, here also when the current was flowing in a anti-clockwise direction, the deflection was this way. When it flowed in clockwise direction, the deflection showed this. So the compass needle deflection reversed. Magnetic field due to a current through a straight conductor. This is a straight conductor, like in the Oersted experiment. Okay, in this experiment there is a variable resistance, there is a current ammeter, this is the battery. When the current is increased, the deflection also increases. When means suppose we say the potential difference applied is 50 volt, then this would be a circle. When the increased 100 volt, this would be the same, but its in power would increase. Means the magnetic field in this area as compared to previous one, it would be more powerful in this area. When the volt was 50 volt, if it is small, then when you compare with 150 volt, it will be very large. When a current is increased, the deflection also increases. Indicates that the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. When the current is increased, the deflection also increases. It indicates that magnitude of the magnetic field produced at a given point increases when the current is increased. Current in the wire is increased. Here the compass is placed at point P. When the compass is moved to another position, let us consider here Q. We see that deflection in the needle decreases. Here the deflection in the needle decreases because it is far away from the center, from the conductor. Thus the magnetic field produced by given current in the conductor decreases as the distance from it increases. As we have increased the distance from this, so the deflection has increased. Deflection has decreased. From figure, it can be noticed that concentric circles representing the magnetic field around the current carrying straight wire become larger and larger as we move from it. So as you can see also, the circles diameter keeps on increasing. As we move from it, we become as the representative of the magnetic field around a current carrying conductor becomes larger and larger as we move away from it. The pattern of concentric circles indicating the field lines of a magnetic field around a straight conducting wire. The arrows in the circles show the direction of field lines. The arrow circles show the direction of the field lines. Right hand thumb rule. This is a simple, easy way of finding the direction of magnetic field associated with the electric current. If we consider this right hand thumb, if you placed it in this direction, then the thumb will show the direction of the current, and this position, this will show us the magnetic field. Okay, this is nothing but this is a simple rule so that we can follow it easily. Follow the magnetic direction of magnetic field as well as current easily. Magnetic field due to a current through a circular loop. We know that the magnetic field produced by a current carrying straight wire depends inversely on the distance from it. If the distance is increased, then the magnitude is decreased. Similarly, at every point of a current carrying circular loop, the concentric circles represent the magnetic field around it, and it becomes larger and larger as we move away from the wire. When we means the concentric circles, as you saw also in the previous slide, that concentric circles keep on increasing, but when the close to it, it is very small. When we move further away from it, the concentric circles keep on increasing. By the time we reach the center of the circular loop, the areas, arcs of the big circles would appear as straight lines. Here, as you can see, means when we appear towards the center, this is, let us consider this as a center. Okay, this is the center, I guess. So here you can see that the circles is very small, but when you come towards it, it is creating a straight line. Okay, this is by the time we reach the center of the circular loop, the arcs of these big circles would appear as straight lines. Every point on the wire carrying current would give rise to a magnetic field appearing as straight lines at the center of the loop. By applying the right hand rule, means that we can easily find out check every section of the wire that contributes to the magnetic field lines in the same direction within the loop. By the right hand rule, we can easily find out the direction of the current. Means if we know, we should know the direction of the current, by applying right hand rule, we can easily find the direction of the magnetic field. This, okay, just a sec. This is the circuit diagram. This is the circular loop. This side is connected towards the positive side, and this is the negative side. This side of the positive side, you can see that there is the anti-clockwise movement of circles that is around the wire. This side, when you come towards this side, then you can see that the circular direction has changed from anti-clockwise to clockwise, because simply the current of flow in B side is like this. So this is the direction. When you come from this will be the direction. So the direction has changed. This is the setup, this is the battery, this is key, and this is the direction of flow of current. If there is a circular coil having n turns, the field produces n times as that produced by a single turn. If you consider a single turn circular loop, then the field produced would be 150, I guess. And when it is n turns, that it will be 150 into n. This is because the current in each circular turn has the same direction, and the field due to each turn then just adds up. Magnetic field due to a current in a solenoid. A solenoid is nothing but a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. You can see the picture this side, I guess. Yes, this is a solenoid. And around a cylindrical shape, the wire is wounded in this direction. This is a solenoid, current carrying solenoid. The field lines inside the solenoid are in the form of parallel straight lines. This indicates that magnetic field is the same at all points inside the solenoid. You can see the magnetic field lines. They are not parallel to be, they are close to parallel. As you can see here also, means the rays that are coming would not be parallel, but inside it they would be parallel. This indicates the magnetic field is same at all points inside the solenoid. That is, the field is uniform inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron. When placed inside the coil, the magnet so formed is called electromagnet. This is by using a magnetic field to a current in a solenoid, we can create a electromagnet. This is the field lines of the electric field through a current carrying solenoid, and this is the current carrying solenoid is used to magnetize a steel rod, inside it an electromagnet. This can be created to a electromagnet. That will be all for today. Thank you.